Welcome to Physiology Raw. This is a first essay question for exam 4. I drew out some pictures to help speed up the process. The first part of the question says, explain the solutes water. Explain how solutes in water are reabsorbed into the kidney tubules. Be sure to include the reabsorption of sodium, glucose, water, chloride, etc. Include your discussion how various solutes are reabsorbed and the concentration or concept of renal threshold and saturation. So here I drew this is the glomerulus, so the afferent arteriole will come in and form a capillary bed that's right up next, or inside, I guess, of the Bowman's capsule. And right here, a lot of things are going to be pulled from the blood into the fluid in the capsule. So this includes water, various ions. We got some peptides, amino acids, and just a lot of almost everything except for like whole cells and blood proteins. Yeah, and so we'll talk about that here eventually, but we'll just continue on this one. Even glucose, glucose goes through here, glucose, and so that's behind this yellow, or this red line right here. And so in between, this is the proximal convoluted tubule, which a lot of things are quickly pulled back out of the fluid back into the blood. As you can see, this efferent vein or arteriole will circle all the way through. I guess I could just like that. Oh, not inside. Whoops. Just like that. And so in here, things will be pulled from the fluid back into the blood. This is going to be, of course, the glucose has to get pulled back out. Some ions will come back out as well. That includes will include some of that sodium, potassium, and other things. The amino acids that got pulled in will shoot back out, and of course some water. Water, pretty common thing that goes back and forth. So once it gets to the descending limb of the, I think it's Henle loop, this section, only water will leave to go back out. So H2O is reabsorbed, back into the vein. I guess I can go like that. And so it becomes more like outside here, as it goes down, will become more salty. So it has a lot of sodium and chloride, and also I think urea will be in high concentrations out here. So water will leave the fluid. But on this side, after this purple dotted line through here, water is no longer permeable. So H2O, no more. So that means the stuff leaving the fluid is going to be that sodium and chloride, sodium chloride, and I think that's actually it. So sodium chloride are going to leave in that area, right? And as it reaches back to the top, then maybe some, no, actually, just like that. And so past this green, again, some more ions will leave. So that's going to include ions such as sodium, calcium, and chloride, but also water sometimes. And that is controlled by aldosterone. So if we are very dehydrated, our body will release aldosterone, which will allow water to be pulled back out of the collecting duct. This is the collecting duct at this point. Through here is the distal convoluted tubule, which I guess I should say. Oh man, I forgot to have a dotted line through there. Try to use yellow. So here H2O will come out, some water, other ions, and that's all controlled by different hormones that our bodies will different hormones that our body releases. So, some things are like that diuretics or antidiuretics as well. Diuretics, I guess. Oh, that's not how you spell that. Diuretics. But you get the point. It's diuretics, and then also through here, thiazides will also control that, but in the negative. So if there's a thiazide, this stuff will stay inside of the fluid. If it's a diuretic, then it'll come out. Okay. So the concept of renal threshold and saturation. So, like I said earlier, glucose is a good example of this. Glucose. So, glucose usually is 100% reabsorbed right here in the proximal convoluted tubule. But if there's so much glucose in this fluid, there's little proteins that need to transfer glucose back out. Sometimes those get oversaturated. It's too full. So some glucose, I'm just gonna put a little G to signify glucose, will just escape and keep moving down. And so if renal threshold, so if how do I say that? Let's say proteins become saturated and can't pull back all the glucose, or there's a few other things that need to be pulled back, but sometimes it just gets so full it can't do it, and so it escapes and gets lost and excreted through the urine eventually. So the filtration, that's this one right here. So the first level of filtration is going to be the endothelial cell. So that like kind of just endothelial cell of the endothelial of the vein of the arteriole. So that's the first line of defense. It's fenestrated. So it has holes in it. It's supposed to be a hole, and so but these holes are really small, about 70. I don't know. They're very small. So the point of them being small is so that no cells plus blood proteins. Let's go blood proteins. Can't get through. So that holds that out. This blue one is now the basement membrane. Let's go basement membrane. And so this one has a charge to it. So let's go charged. And so a lot of proteins are negatively charged. So this basement membrane helps to make sure that no charged particles, except for like the ions, because they're small enough, but no larger sized charged molecules can get through into the fluid in here. And then the last line of defense are these podocytes or podocytes. So this is the last line of defense. Last line against size and charge. So usually it's, charge is a big thing. They don't want to get a whole bunch of negatives. That's because the blood proteins are usually negatively charged. There's actually a disease that runs my wife's family called Alport's, and they have an issue with the basement membrane, and so it's either poorly formed or doesn't form at all, and so they, without taking medicine, they'll end up dying the males will end up dying very young, because either this basement membrane doesn't exist and everything gets through, which is bad because you're losing glucose, you're losing peptides and amino acids, stuff like that, or the basement membrane will scar over, and so nothing will get clean. So very, very poor situation. But luckily modern medicine has increased their lifespan from only about 30 years to much older, especially if they take care of themselves. But took a deep dive in that, so discuss the pressures. So here's some pressures. Okay. Right, let's see. Hold on, what does it say? Discuss how blood. No. In your discussion, describe the filtration membrane in the renal corpus and pressures involved in filtration. So here's the pressures over here. Okay. And so we got a few colors going on. So as we saw earlier, BCOP, so that's the blood colloid osmotic pressure, pretty much. That will pull water and substances back into the bloodstream. Because those proteins, like I was saying earlier, can't get through, and so it'll make osmosis go into that way. And then we have let's say HP. So this is hydrostatic pressure. So as blood comes in, it creates the hydrostatic pressure that will push water into this, water that way, and then hydrostatic pressure of the capsule. So things, the fluid and things that are already in here, pushing the water back out. So even though we have two arrows going this way, this is very strong. This osmotic pressure is sustained to be about 55 milliliters of mercury. Well, the B cup stays at that 30 mmHg, and I think this one was actually 15 mmHg. So what is sustained, well, I guess I could just so about 20, so 20. I don't know. So as you can tell, with these numbers, most of the pressure is going to be coming towards the capsule. So water and other substances are going to want to be in the capsule instead of just the arteriole. So blood flow on this. So the efferent and afferent and efferent are the the arterioles that either go in or leave respectively. So what we could do is, if we dilate the afferent, then we could get more blood flow into here, which will increase that pressure to cause more of this pull, cause more things to leave the arteriole and go into the capsule. If we constrict it, however, then less blood could get through, so maybe not so much gets filtered. The opposite is true for the efferent. If that one dilates, then blood is easily able to pass through and keep on going. And then if it constricts, then there's a buildup of blood in the glomerulus that causes higher pressures, so it will be able to be filtered easier. So blood flow or blood pressure regulation is definitely a high thing that could affect the filtration rates. Describe what GFR. GFR is, and explain the principle of clearance and how it is used to estimate GFR. So GFR is, I guess, GFR, I forget. I think I'm going to start with clearance first. Let's just do clearance. Can you see all the way up here? Cool. So clearance has a cool equation to it. So clearance equals oh, that's a U right there. Okay. So if there's a substance, we could measure the clearance of that substance from the concentration in the urine multiplied by the volume of urine divided by the concentration of that same substance in the plasma. So you have to take a blood sample and a urine sample, and then comparing that will help us understand how well the kidneys are clearing a certain substance. There is some substances that are by just one pass, the kidney is going to pull everything out, and it's not going to reabsorb it back into the blood, it won't reabsorb it back into the blood, and it'll all be secreted out of the urine. And then there's other things that will like glucose. So glucose would be very poor to check clearance, because glucose is completely reabsorbed back into the blood. The GFR, however, is to measure like how much blood is filtered period, I guess. I think that's that glomerulus filter rate. And so there's some substances that are they get pulled from the glomerulus to the capsule, and they aren't reabsorbed or secreted in any strange amounts. So everything that gets absorbed at the beginning stays and gets secreted. So we could test that. We could take those measurements and see how much blood is getting to the kidneys, which it could be very helpful. If there's not a whole lot of blood getting to the kidneys, we know there's an issue. So let's see. A good substance to measure GFR is inulin. This doesn't get reabsorbed, secreted, degraded, or metabolized by the kidney. So we could test that, and we can see how well the kidney's doing. And I think that is the end for that one. That's all I gotta say. Hello, welcome to essay question number 2 for Unit 4. The questions asks us to explain the tubuloglomerular feedback. So the glomerulus is the capillary bed right here, and then the tubule is the Bowman's capsules begin of the tubular parts. And so what happens is they communicate with each other, and it will affect the function of the kidney as a whole. So we look for I guess I'll just make a quick little list. Glomerular filtration. Oops, that's not here. Filtration. And so that is going to affect how much blood is filtered in the glomerulus. There's the flow sense, which also, there's the communication of flow to see how much blood is getting pushed through, ions. that are getting tested and checked to make sure all the ion flow is right. And so through that way, these two separate parts are able to communicate with each other to make sure that enough fluid is getting, enough fluid or particles are getting retained or secreted through the urine. And as we continue, we'll be able to see that in a little bit more detail. The second part is explain the renin and angiotensin and aldosterone system. So this is part of the RAS system. So RAS, which starts with angiotensinogen, which is a protein, plasma protein produced by the liver, and then renin plus renin. And this is secreted when there's a low GFR. Remember, GFR is the glomerulus filtration rate. So this could be low filtration sensed by the afferent arteriole, or a low blood pressure sensed by baroreceptors. And we'll talk about baroreceptors in a little bit later. But that will produce, so renin and this, the cleavage will produce this angiotensin 1, and then that will interact with ACE, which is a angiotensin converter enzyme that will create angiotensin 2. And so this one has a few different effects on a couple things. So we'll just say the first part goes to the first two goes to increasing GFR, and so we could do that by increasing GFR, which so part of that chemical goes to the brain, which helps us feel thirsty. So thirst plus salt to increase filtration, absorption of the kidney and filtration, obviously. And then the other part of that, so here's one, let's go like this. It's going to be going to the kidneys, and then that will constrict the efferent arteriole. So that will increase the pressure. So if we constrict this right here, this will increase the pressure. So P will go up. And so increased pressure means that more solutes and water will go into the Bowman's capsule to be filtered. So that's two things that it does. Maybe I'll go like this real quick. Let's go 1, 2, and then it could also go 3, which it'll go to the adrenal gland to produce aldosterone. And in a second we'll talk about what that does up here, but aldosterone basically makes a certain area, let me just do this. So it raises more salt, so more salt right there. And later we'll explain it, but it'll it works on these sodium potassium ATPase to raise more salt below this line, which linked with something else will increase water reabsorption. And then lastly, so 4, it'll cause system-wide vasoconstriction, which increases filtration. I guess I could go up with that right there as well, but it basically just increases the filtration rates. And so that is what that does. Describe what happens to cellular level with the ADH and aldosterone. So ADH, we'll start with aldosterone because I alluded to it earlier. So aldosterone, what that does is it also responds to increased K levels, but it creates more and puts into hyperdrive the NAK-ATPase protein channels. So what that does, again, if we have more more of those protein channels on the ascending portion of the loop of Henle, then we have more salt. So again, more salt here. So if more salt here on the descending portion of the loop of Henle, more water, because these little aquaporins will pull more water out. And when we're pulling water out, we're putting it back into the blood. And so ADH ADH affects the collecting ducts over here. Is the collecting duct, and that will put in more aquaporine channels. This is aquaporine 2. Aquaporine 2, I'll just call it AP2 channels, which because we made it more salty out here, the water will follow and help us retain more water. Insert of aquaporine. And so we fill that through two. I'm gonna talk a little bit more about ADH. Let me use a different ADH. So that is felt by osmoreceptors. So this is in the brain, receptors. So these respond to increased ions in the blood, which is a sign of dehydration. So those will send signals to release ADH, which puts in these extra aquaporins over here, and then also will respond to baroreceptors. Baroreceptors. And so if there's an increase in blood volume, so if blood volume increases, then it will inhibit ADH, which means that these aquaporins will go away, meaning that more water will just pass through, get secreted through the urine. But if blood volume is low, then it will also release ADH. And as I said earlier, more of the aquaporins right here, will help us reabsorb water. Oh man. So let me see. So, as I alluded to earlier, we're talking about the loop of Henle. Explain how the loop of Henle is used to establish and maintain the renal nodular concentration gradient. So in the earlier episode, right here, this is going to be O2 can pass through the wall here, but in this region it can't. So I'm going to say all the way up to this portion. So O2, no way. Only salt can come out. So because it's like more salty out here, more water's leaving. until it gets to the bottom, where then it's finally isoosmotic. And then as it travels back up, now it's no longer, water can no longer leave. And so to keep that isoosmolarity, because as you go higher, it's less, less salty. So more of the salt will be pulled out through it looking for equilibrium. So more salt will leave. Right? Gradient, yeah. And so we could then control the water permeability and salt permeability on this side to help that's part of the next part. Explain how this gradient and ADH can work together to excrete urine of different concentrations. So let me erase a few things to try to make it a little bit more clear. Oops, a little green. So if we are dehydrated, let me make it purple so we can follow it a little bit. Dehydration. So if we're dehydrated, that means we want to keep more water. So what we could do with aldosterone, kicking these sodium potassium ATPase into hyperdrive, creating more salt right here, then we could put in more of these aquaporons from the ADH release, right? So if we put more in there, then we could have water, follow its gradient or osmosis, right? And it'll leave to get back into the back into the blood. And so that's how, if we're dehydrated, then we can manipulate those two things to help us stay to maintain the water we do have. But if we're very hydrated, I wonder if I could put this in red actually. So hydrated. Then what we could do is we want to get rid of more of that water. So we're going to take away those aquaporons, and even get rid of aldosterone. Yeah, if we get rid of aldosterone, then it's less salty. So I'll just erase that. So as we go down, water, since it's less salty out there, water doesn't feel like it has to leave as badly, and so more water will stay inside of the tubules and be secreted out of the collecting duct without it being reabsorbed back into the blood. And so that's what happens when we're hydrated. Okay, I think different concentrations. Yeah, so that's how that works. Working with ADH, increase aquaporons, decrease aquaporons, it all works together. That's all I got to say about that one. Welcome to question 3 of Unit 4 exam for Physiology Raw. In this one, we're talking about some lungs and so the first part says, explain how the membranes, pressures, and mechanisms that make a negative pressure ventilation possible. So over here I have a little diagram of the lung, just of the one side. So the green, or I guess the black, right, is the lung itself. The lung itself, the outside layer of the lung. The green is going to be the visceral pleura. The blue space in between, so the color blue is representing something else, but Actually, let me jump to purple. I'll talk to blue. I'll talk about blue in a second. Purple is going to be the. It's also a pleura. It's the parietal pleura. So there's these two membranes up against each other, and it has a little bit of space, and in that little space is the pleural cavity, and in that space it has a little bit of fluid. So it's got this fluid. And so what the fluid does is it maintains a slight negative pressure, about negative, if I remember correct, -4 millimeters of mercury. And so it's like when you have two glass panes next to each other, and it's really hard to pull them apart this way, but it does allow for a lot of side-to-side action, nice and smooth. And so right here, this red is the diaphragm. And so for resting breathing, we have the diaphragm flex. So that means it goes straight instead of bowed upward. It goes straight. And what that does is it creates even more negative pressure on this pleural cavity and the fluid within. And so that, because we can't rip it apart like this, it'll expand the lung. The lung gives out, and so it expands that. And so we see that with other musculature, such as the intercostal muscles, and when we're really breathing, even the pec minor and scalenes. But usually it's just the diaphragm creating more negative pressure in that pleural cavity. Describe the pneumothorax and how it occurs. So a bad thing that could happen is if we either get too much fluid buildup in here, or a hole is created. So now we see that there's no pressure being held. So I guess. And so what that means, the lung itself is elastic, has this elasticity. So that will make the lung collapse. And it'll get real small. Because it doesn't have that, negative pressure any longer. And so either fluid buildup or a puncture, a sucking chest wound, bad news bears. We have to cover up that hole and try to re-get that, or pump out that fluid to get back that negative pressure, which, yep. So surfactant. So moving over to here, here's a little diagram of alveoli. Maybe I'll label it. Alveoli. So in the alveoli, there is these little water molecules, and the water molecules they have a surface tension that wants to bring everything together. So usually, we'll see this action. And so you can see that there's two different sizes, and when we hook up two balloons on two different sizes, we would think that the air would equalize, so the balloons would be as the same size. But because of this tension of the water molecules, we actually see that the air will start going into the bigger alveoli. So what we produce to counteract this is something called surfactant. So surfactant is kind of like putting soap in water. It'll break that surface tension, and so that way we are able to expand this without having to use as much force. And then if a higher concentration of surfactant is on one side, then we could get both of these different size alveoli to expand appropriately. That's what surfactant does. Okay, and then so now we're going to talk about CO2. Oh geez. CO2 and how that is transported. How's that transportation in the blood? So CO2. So some of it, after being diffused through various layers of the alveoli and into the bloodstream, 7% of it will go straight into the plasma. A higher percent, 23%, will be picked up by the hemoglobin amino acids. So not where the oxygen binds, but a different location. But most of it, solid 70%, will be converted to HCO3, so bicarb, through the mechanism that does that. And then oxygen, we'll put oxygen up here. So very little of that will go straight into the plasma, only 0.5% straight into the plasma. But we have the rest, that 98.5%, goes in to bind into the hemoglobin. The hemoglobin has 4 subunits with an iron in the middle of each subunit, and that holds on to the iron holds on to the oxygen, and then that each red blood cell has a bunch of hemes. Okay, so now we have this curve right here. This is the saturation percent of oxygen and the partial pressures of oxygen in the arterioles. With that, we see, so usually this is just the normal affinity for oxygen to that heme. So let me think. Yeah, okay. So we'll start with things that will affect this curve. This green line shows less affinity of oxygen to heme. And so, I'll write that, less affinity for O2 by heme. So we see things that cause this would be the R state of, oh no wait, sorry, not the R state, the T state of heme. T statement, the tension state, means that the hemoglobin is less likely to bind to oxygen and actually tries to push it off. High CO2 levels, higher acidity in the blood, which is found in the tissues. So is CO2. A compound 2,3-DPG, which binds in the middle of that 4-heme complex I was talking about, that makes O2 disassociate. Exercise, and then temperature. Oops. So all these going up will make the affinity for O2 by the heme go down. So things that make that go up, affinity for O2 by heme is going to be the opposite of most of these. So you have the R state, the relaxed state of heme. We have so like low CO2 levels, basic pH of the blood, no or little 2,3 DPG, rest, so rest, no exercise, and then low temperatures. And so that will make affinity go up. Alright, and I think that'll do it. As you can see, there's kind of a flat portion right here. When one oxygen binds to hemoglobin, it actually helps the other subunits of that heme bind with more oxygen, but when one oxygen comes off, it'll increase the other hemes to kick off their oxygens. So it's a very dynamic compound, dynamic protein. And I think that's it for number 3. So this is question 4, part 1 for the essay questions for exam 4. Feeling pretty tired, so I think I'm gonna break these up into parts. So the first part of it is explain Dalton's law. So Dalton's law, and that one is so the pressure ATM is equal to the partial pressures of X, Y, and Z. So this X, Y, and Z could be nitrogen, oxygen, CO2, or anything else that is a gas. Henry's law is when gas comes in contact with water. I'll use that as a diagram in a second. So that is equal to pressure of the gas times some coefficient of solubility, and that's going to equal is it dissolved gas concentration. And so how that affects the O2 and carbon dioxide, CO2. So we see in a closed container there's going to be some level of oxygen going into the solution, to some level, and there's going to be some level of carbon dioxide that goes into that solution. If we start putting pressure, so if we increase pressure down on this plate, then we'll see that more of those gases will leak or dissolve into the solution. But due to and so that's just part of Dalton's law. Dalton's law explains how much pressure. So how much pressure comes from each individual gas, and Henry's law tells us we could take the pressure of oxygen, plug it into Henry's law, and then use the coefficient of solubility of that certain gas. So if I remember right, carbon dioxide has a higher coefficient of solution than oxygen, so it'll dissolve more with less pressure that is required. Yeah, okay. Explain the alveolar gas equation. So I will write that out in the different parts. So the alveolar gas, so P of the alveolar, so pressure of the alveolar O2 equals so Fi, so that is the fractional concentration of inspired oxygen, and then the pressure of the atmosphere minus pressure of H2O, and minus PaCO2 over R. Okay, so this is the the O2 in the, so Fi, O2 in atmosphere. And so since there's a level, there's some water in the lungs itself, we have to subtract that pressure from the pressure of the atmosphere, because the water interferes with oxygen moving out of the alveoli. And then there's already some CO2 inside of the vein there, and it's also trying to go, so CO2 is trying to go that way. Well, I'm gonna close O2. Dang, that's not gonna work. O2 is going this way. And so usually this is 21%. And so, like, for example, if we give a patient much higher percentage, we suspect that this right here would go up as well. But if we see that it stays, or it achieves like a normal, what we would suspect to be a normal pressure of oxygen, then we'd know that something's wrong. Yeah. And so this R is a ratio, so the respiratory quotient, quotient, and that's the CO2 over O2. So this is a CO2 that we produce in the body. It's like metabolism. And then this is yeah, and so I said this is the pressure of CO2 coming out of the arteriole. Yep. So ventilation and perfusion ratios. So I'm going to use this again. Yeah. Ventilation over perfusion. And so that ratio is going to help us understand. It's going to give us another dynamic of understanding the blood concentration of oxygen, how much air is getting into here. So there's a concept of dead space. So anything above here is dead space, and that will stay the same no matter how much we breathe in. So if we breathe in, 500 milliliters of air, 200 milliliters of dead space will still be there. Or if we breathe in, was it like 700 milliliters of air, we're still gonna expect that 200 milliliters of dead space. And so perfusion. So that's kind of like the ventilation. So if something that reduces how much air gets into the alveolus, or if the alveolus loses surface area, that's going to make the ventilation go down. So maybe I'll take a little note of that. Air getting to alveolus, or air getting to alveolus, or alveolar. Dang, dude, really? Surface area reduced. Okay. Can you even see yellow? And so with the perfusion rate, perfusion is how much blood. Can you see that even? Barely. Jeez. Perfusion is how much blood gets to the alveoli. And so if we got some kind of blockage over here, so blockage, that will reduce it. If like the capillary collapses, you know, that will definitely reduce perfusion rate. If there's a vasodilation, then we'll increase perfusion rate. So this ratio will just help us understand where the issue is, if it's in ventilation or if it's in blood flow, and if we don't get the ratio that we're looking for, which I think should be about 1, then we know like that there's an issue and where to find it. So I think that's going to be the end of part 1. So this is part 2 and 3 of question 4 for essay questions for exam 4. Part 2 says, explain total pulmonary and alveolar ventilation rates and describe why slow deep breaths are more beneficial than rapid. So let's define some of these rates. So total pulmonary, right? Total pulmonary ventilation is going to be equal to breaths per minute multiplied by the tidal volume. And tidal volume is how much air. So tidal volume is equal to air pulled in and pushed out for every breath. Okay, so this is all the air that is going in, and all the way out through here to the other side, all the way through the various levels of the bronchi, and finally into the alveolar sacs. The issue arises because of alveolar ventilation. It's a little bit different. Alveolar ventilation. So that's going to be the tidal volume minus dead space. And then that's going to be multiplied by breaths per, or the breath rate. So we have the tidal volume minus this dead space. Dead space is defined as everything that's not alveolar sacs. So as you can imagine, you know, air has to come into the trachea and down the bronchi. The issue is the bronchi can't participate in gas exchange. So that's why we have to let this dead space is equal to like the bronchi, no gas exchange. So no matter what, for example, say there's 200 milliliters of air that is just dead space. No matter how much you breathe in, you have to take away these 200 milliliters of dead space. So if you have short, shallow breaths, and say you take in 500 milliliters each breath, you have to take away that 200 milliliters, leaving you with that 300. Or if you take slow, deep breaths, maybe you take in 800 milliliters, then you minus that 200 milliliters, and then so that's going to leave you with 500 milliliters of air that's able to take part in gas exchange. And so taking slower deep breaths allows you to get more air to allow you to do gas exchange. Short breaths, maybe eventually you'll reach a high enough level of air able to do gas exchange, but it's going to take longer and it's going to take more energy. So it's better to take long, deep breaths. So that's part one, or part two, I mean. And so part three describes COPD and restrictive lung disease. Between the two diseases, mention what emphysema would be, and then explain mechanisms of trapped air in emphysema. So I got a few graphs over here. We get some space going. So I'm going to start with this normal. So this is normal up here. So we can see that intrapleural pressure. Remember at the beginning I was talking about that space in between the visceral pleura and the parietal pleura. And so if you increase the pressure, it'll eventually increase the lung volume size. So at the beginning we see that takes more pressure to increase the volume, and then after a while there's this the alveolar sacs will start expanding more easily. You see it shoot up right here. And the reverse is true for exhalation. So when we see restrictive lung disease, we see that maybe it doesn't have. So let's go less surfactant. So now it takes more pressure, more energy that we have to create through our musculature, our diaphragm, and our intercostal muscles. More pressure to get that lung to finally fill up a little bit. And so this is characterized by struggling deep breaths. You really have to put effort to get air into your lungs. So we could say that it's lacks compliance, so no compliance. While the opposite for let's see. COPD, so that's COPD / obstructive lung disease. So this is obstructive, that's what the lung disease. So in this graph you can see that it looks normal pulling in air. You suck in, you have to create a little bit less pressure than the normal, because this one has too much compliance. It's actually lacking in elasticity. So elasticity, circle that, put an X through it. So this is characterized by maybe when you're exhaling, it's not enough just to relax your diaphragm and your intercostal muscles, because there's not enough elasticity in your lung. So maybe even the alveolar sacs are damaged. Alveolar sac damage, and so it could be less not too much surfactant, but not enough surface tension. And so if your alveolar sacs they're damaged and they start combining, now you have a bigger sac, but it's there's less surface to have surface tension. So now maybe you have to hunker down and flex your abdominals to push all that extra lung volume out, or even create positive intrapleural pressure by flexing your abs and really blowing out. So this blows. Yeah, I would imagine obstructive lung disease blows. Emphysema is just that, is the reduced elasticity. And so air trapped inside would be, so since you can't, the lung isn't elastic, air gets stuck inside of those alveolar sacs and it doesn't want to leave. And also the air already in your bronchi, it's harder for that to leave because there's no elasticity in your lungs. So that's that air trap. And so now if you have oxygen depleted air stuck in your lungs, it's going to be harder. You're going to have to work harder to get that good oxygenated air into your lungs because there's already, bad air inside. And I think that will do it for parts 2 and 3.